So continuing on, next we look at the output control devices. So first, here are the symbols for the output control devices. You can pause the video and look over these. I'm not going to go over them one at a time, but these are the kind of things that you would be doing for a PLC when you're looking at the output. So for an actuator is a device that converts an electrical signal into mechanical movement. An electromechanic solenoid is an actuator that uses electrical energy to magnetically cause mechanical control action. Solenoid valves are electromagnetic devices that work by passing an electrical current through a coil, thereby changing the state of the valve. Stepper motors rotate in discrete increments when electrical command impulses are applied to it in the proper sequence. So that would be something be useful. Every revolution is divided into a number of steps, and the motor must be sent a voltage pulse for each step. The amount of rotation is directly proportional to the number of pulses, and the speed of rotation is relative to the frequency of those pulses. So you can see how that would play out well for the number of steps. Stepper motor, open loop, the servo motors operate in closed loop mode, while stepper motors operate in open loop mode. Open loop is control without feedback. For example, when the controller tells the stepper motor how many steps to move and how fast to move, but does not verify where the motor is. For servo motors operating in closed loop mode, the closed loop control compares speed or position feedback with the commanded speed or position and generates a modified command to make the error smaller. The error is the difference between the required speed or position and the actual speed or position. This is an illustration showing the typical closed loop servo motor system, and so you can look in the textbook for more information about that. For CLN circuits, CLN circuit is a method of maintaining current flow after a switch has been momentarily actuated. Here in the picture, we have an example showing a hardwired CLN circuit. Here is an example of a programmed CLN circuit, and you can refer to the textbook to see a little bit more about that. For electrical interlocking circuits, first we have a sequential hardwired control circuit. So for an electrical interlocking circuit is used to prevent a piece of equipment from operating under certain potentially hazardous or undesirable conditions. Useful thing. Here is an example of a program equivalent sequential control circuit. And so you can pause the video and look at that and get a little bit more perspective on that, or look at the textbook. For a push button interlocking, it is one of the methods of preventing two loads from being energized simultaneously. The hardwired push button circuit is designed to prevent solenoids Sol A and Sol B from being energized at the same time. Let's look at latching relays. Electromagnetic latching relays are designed to hold the relay closed after power has been removed from the coil. The latch coil is momentarily energized to set the latch and hold the relay in the latched position. The unlatched coil is momentarily energized to disengage the mechanical latch and return the relay to the unlatched position. For OTL and OTU, the PLC output latch, OTL, and output unlatch, OTU instruction duplicate the operation of electromagnetic latch relay. So the OTL and OTU instructions have the same address. The OTL instruction can only turn a bit on, and the OTU instruction can only turn a bit off. Here we see the hardwired and programmed latching circuits of how they would look. And so you can be thinking about that as you're considering how you're going to be doing your PLC programming. Let's look at a process used to control the level of water in a storage tank. For a manual mode, the pump will start if the water in the tank is at any level except low. For an automatic mode, when the level of water reaches the high point, the pump will start. When the water reaches a low point, the pump will stop. Here is an illustration of a program used to control the water level. You can see how some of these programs are getting a little bit more complicated, but you can look at the textbook or pause the video to think about that more. For converting relay schematics into PLC ladder programs, a sequential control process is required for processing that demands that certain operations be performed in a specific order. In a filling and capping operation, the tasks are fill the bottle and then press on cap. These tasks must be performed in the proper order, as you can imagine. Combination controls require that certain operations be performed without regard to the order in which they are performed. Here are the tasks: place label 1, place label 2 on the bottom. The order in which the tasks are performed does not really matter. For automatic controls involves maintaining the desired set point in an output. When maintaining a certain set point temperature in a furnace, if there is a deviation from the set point, an error is determined by comparing the output against a set point and using this error to make a correction. So here we're showing a sequential process control for a relay schematic. So 1, you have push the start button. 2, the table monitor is started, and 3, package moves to the position of the limit switch and automatically stops. So this was something that you could see that you could do. Here's a sequential process control program where you can review and see how that works. Here we're showing the instructions programmed for an optimum scan time. The series instructions are programmed from the most likely to be false to the least likely to be false. The parallel path that is most often true is placed on the top rung of the list of rungs that you would have. Here we have a hardwired jog circuit with control relay, and you can refer to the textbook if you'd like to explore that further. And here is an equivalent program jog circuit, so you can go back and forth between those to compare them. Next, let's look at our writing a ladder logic program directly from a narrative description. So let's look at drilling. So a drilling process that requires a drill press to turn on only if there is a part present and the operator has one hand on each of the start switches. So this is getting close to CNC, which were covered in the other part of this course, but keep this in mind. What about a garage door, an overhead garage door? A motorized overhead garage door is to be operated automatically to present preset open and close positions. So this is the logic that would be necessary to be doing that. And I'm not going to go through this, but you can pause the video and see if you agree with this logic, or get some perspective on maybe there's something that you didn't realize would be something important. For a continuous flow operations, this process requires that boxes move on a conveyor be automatically positioned and filled. So that's what that is, and here is the associated program to be able to do that. Let's talk about instrumentation. So instrumentation is the use of measuring instruments to monitor and control a process. It involves the design and calibration of systems used to measure, record, and control industrial process variables. Variables may include pressure, temperature, flow rate, weight, and chemical consistency. Every instrument has at least one input and one output. So here we see a pressure input, and then you see an output that would be corresponding to that pressure. For a pressure sensor, the input could be some fluid pressure and the output a 4 to 20 milliamp current signal. For smart instruments that contain microprocessors that have built-in diagnostic ability, greater accuracy, and ability to communicate digitally with host devices for reporting of various parameters. And on the bottom, you get a chance to see one way of trying to capture that capability. You can also have receive, process, and send signals. The PLC role as part of an industrial instrumentation system is to receive, process, and send signals from input to the output device. With the use of programming software, the PLC can control, monitor, and display all the parameters associated with a given process. All right, well, thank you very much. That'll end it for this chapter.